In the previous video, we set up the model for exercise A1, as you can see on the screen now, and we could start the simulation, and the model went till the end without any error. So now we are going to try to look at the results, especially the results that we want to compare with other parts of this exercise when we want to have some comparison due to changing the parameters. To do that, of course, I'm still in Delft 3D with the same working directory that I was before. I need to start QuickPlot. The QuickPlot you can start it from here because it takes usually some time. I have already opened it. So now I have QuickPlot. I can open the output of my simulations, the first simulations that I had. If I click on this button, and if in this part here I have Delft 3D output files, it shows me two output files that I have. You know these output files. One is history file and one is the map file. So I open both one by one. So I open the history file and then I open the map file. Okay, map file is also open. Now I have both files here. The first thing that it is nice to just take a look is the changes in the morphology. So I go and then choose in the map file bed level in water level points, and I change this to XY is here and continuous shades. So you can from patches, you can change this to continuous shades. And if you click on quick view, you can see that at the end of the simulation, you can see some channels forming at the end of this flume that we simulated. Yeah? So there are some bed level changes. But okay, in any simulations, you can see these bed level changes, but it's important to see if the model is working properly or not. To check that, I go and choose my history file. And in the history file, I had different observation points and one cross section. So first I will look at my observation point. The first observation point, which is towards the upstream. And if I look at the water level here, I can see that the water level goes up and then it is constant a bit lower than 5 meter. Yeah. So more or less the hydrodynamic is working okay. Be careful that I'm looking at water level and not water depth. Yeah. So if on the same figure I add the last uh, observation point, so the one which is closest to the downstream, with red, if I add it to this plot, I can see also the water level there is also first with has a jump, which is because of the spin up of the hydrodynamic model. Then it is constant on a bit more than 4 meter. Yeah. So it shows more or less that my model works okay hydrodynamically. One of the other interesting things that we can see if we are looking at the history file is the amount of sediments that passes through the cross-section that I put in the model. If you remember, I put a cross-section in the middle of the model. And if I go to and choose the cumulative total transport, then I have only one cross-section, and I rather change it to black. And if I look at it, it shows me that sediment passes one way in this canal, of course, understandably, and in total during this simulation time, about 10,000 cubic meter of sediment has passed through the model. Again, a reminder that our hydrodynamic time was 2 days, but with morphological factor, we are practically run it for 500 days because our morphological factor was 250. So the other thing that we can also look here is that we can look at the instantaneous total transport. And if we look at that, we can see that it again goes up and then becomes stable, which is because we have a very uniform flow and the sediment passes through this cross section more or less uniformly. So you can see these two figures. One is instantaneous sediment transport and one is cumulative sediment transport at the cross section. And when we change the parameters later, we may compare the result of new models with these values as well. Okay, so these are what I wanted to show from the history file. But again, back to the map file, we can also see some more interesting things if we are dealing with the map file. We saw this. I want to attract your attention here. It says 24 of September 2020. And if I bring this to time step number 1, it is 22 of September 2020. So it is actually for 2 days hydrodynamically. But if we really want to see the morphodynamic time, what we can do is that we can come here, click here, and then change the display time from hydrodynamic time to morphodynamic time. And if I look at the same figure now again, sorry, if I look at the same figure again, which is bed level in water level points, bed level in water level points, I can see that now this date changes to 24 of January 2022. So it now counts for morphological factor and give me 500 days of simulation. Okay, now we understood these difference in the time. I also want to show you a cross section in this model. Yeah, so we are still looking at the bed level in water level points. But instead of looking at the whole map, I want to look at the one line in the middle of this canal in the flume. So then I can choose this, unclick all in the n direction and choose, for example, 6. So it is in the middle of this line. And then here I need to change it to xval instead of xy to x and value. And you can see that now I can should have a color. The color is black in this case. And if I look at time number 1, so time step number 1, this is my initial condition. And now I can change the color to, for example, purple, and look at the last time step, which is 49. 49. And if I add to plot, you can see that the differences between the initial bed level that we had, which was a sloping, and the end bed level, which you can see the effect of these meandering channels that was generated in the model in the bed level at the center line of this model. So you can see these. The other thing that you can do is you can also add water level to whole system. So if I come here and make a water level and add this to plot, so this is also water level at the last moment of this simulation. So now we have water level at the last moment of simulation. We have bed level in the initial condition in black and bed level at the end condition in purple. So now we see that we could run a very simple model with a new sediment transport formulation, which was Engel and Hansen. And now we want to use this model as a base, change some parameters, and then compare the results with this base simulation. Yeah? So this was case 1A. So I can now maybe close these results. I will keep my quick plot also on the window open. The first change that I want to make to this model is to add a second sediment fraction in the same case as 1A. So this new sediment fraction that I want to add to this model is a finer sediment with the D50 of 100 micron or 0.1 millimeter and the initial sediment layer thickness of half a meter. And then I want to try to compare the results. So let's go and see how we can do that. The first thing that I will do, which is also important if you are running different simulations with a similar setup, is to make a new directory. So first I will make a new directory called case 1b. Then I will copy everything from case 1a, which is necessary to run the model. So I do not copy the results, but I only copy all the input files. I just copy them in this case 1b. Yeah? The results, I will leave them here because, of course, this model will change the results. But make sure that you have a new directory and make the changes in this new directory. Before I forget, I also need to select working directory again and change my directory to case 1b. So I'm now in case 1b. I open the flow input that I had as case 1a. I open it, case 1a MDF, open. And now I go to processes, sediment, edit this, and add sediment to my model. Add. So now I have another sediment here. Close. Then I will go to physical parameters, add sediment, and now I see sediment 2 also popping up here. Sediment 2, everything was similar to sediment 1 except the fact that was 100 micrometer, the D50, and the validity or the availability of the sediment of this second fraction was only half a meter. So I also changed these two. Now I can save this new sediment file. I click on save here and make it case 1b, and I save this. So now I have saved the second sediment. I also need to go to boundaries because the transport now also has two sediments. Although we still use the equilibrium concentration for both, we need to again save also our transport condition as well. So I save this as well as case 1b. Save. So now I have these two as case 1b, and the other thing that I will change is the name of the whole MDF file, so the model itself. I save as case 1b, case 1b, just to make sure that I have a different name for that. In the domain also, or the description, I will change this to b, and again save MDF. So now I have a case 1b MDF with the new condition that I wanted, meaning one additional sediment fraction. So let's see if we can run this simulation or not. I close this. Now I come to the Delft 3D, click on Start. Be careful that now it's still on case 1, so I need to browse and change it to case 1b. Open and say OK. Now it hopefully starts running. So you can see that it takes a bit longer than the previous simulation because now we have two sediments. So sediment transport should act at both of these two sediments. So the duration of the simulation is also a bit longer than before. That's important to know this because now we are running very fast simulations. But if your simulation is long, adding another fraction may make your simulation longer. So we really need to make decision if this additional sediment fraction is necessary or not. Okay, so now this simulation is also done. I will close this. Now we want to look at the result of this simulation and maybe do a comparison with the case 1a, our base case. So you can see that case 1 is still open here. I can now go and open case 1b as well. So if I go to case 1b, I have now history for that as well as the map of that simulation. Yeah. So again, let's make a quick look at the bed level in water level points for all the map as contour shades. So if I look at this, so you can see this is now the result of case 1b. And if I go and look at the result of case 1, so the previous case 1a that we had, you can recognize the differences. No? So you can see that this part is very much different now because we have a different fraction of sediment also in the model. So you can see the effect of additional sediment fraction in the result of the simulation. But if you have a sharp eye, you can see that these two times are different. Why are different? Because for this model, I didn't change the time to hydrodynamic to morphological time yet. So if I close this, put it aside, I can again go to case 1b and change the time to morphological time. Okay, so now the times are also the same. Yeah. So it's the exact same time. Be careful that if you are comparing two morphological models with each other, you need to make sure that you are comparing at the exact same morphological time. Yeah. So that's why it is better to change all the showing of the results to a real morphological time. But anyways, you can see how this having a finer sediment changes the behavior of this canal. Here you can see now a deposition. However, here was mainly erosion. Mm. So it is now very nice to see these differences. We can also look into these differences a bit more. One of the things which is interesting to do now, if I close these two, is to look into the cross section that I showed you before. So we want to look at one cross section, number 6, in the middle of these two models. So now I'm first making it for case 1A. So this was case 1A. At the middle, I change it to a black color at the last time of simulation. So you can see that at the last time of simulation, this is what we see in the bathymetry or in the bed levels of this canal. Now, if I change the color, for example, to red and look at the same parameter at the same location at the same time, but for case 1b, and if I add that to plot, you can see how different they are. Yeah. So this is the effect of this very fine sediment that we put in the model, into the model. So you can see that there is some deposition at the end of the model as well. So this is one way to look at these differences. The other way to look at these differences is to look at the amount of sediment transport. So for that, we need to refer to our history file. So there is a history file here. So again, the history file for case 1A, and I am going to look at cumulative total transport. So all the sediment, and you can see that we have only one sediment here, yeah? So I change it to color black, and I look at it. So this is a familiar figure. You have seen it before. Now I am going to turn this into red and then go to the other history file for case 1b. And I look at it. And then here you can see now the both sediments are shown here, and we can also add some to choose sum of all fractions. So this is important to choose this because anyway, we have two type of sediment here. And if I add to plot, you can see that the sediment transport now, because of this very fine sediment that we put in the model, is more than 2 times of the previous simulations. Yeah? So interestingly, it is this fine sediment is washed out of the model very quickly. So there's lots of sediment transport due to that fraction of the sediment. To also see what part of this increase is due to the fine sediment or coarse sediment, we can look at sediment 1 and 2 separately. So if I look at sediment 1 and I make it like in green, okay, and I add it to the plot, you can see that now this sediment, the proportion of the sediment 1 into this sediment movement is lower than the previous model, but the sediment 2, if I change it to color like purple, does most is responsible for most of sediment transport here. So you can see that by mixing these two, because the sediment, fine sediment is moving much faster and it captures the capacity of sediment transport, the sediment 1, which was a coarser sediment, is transported less than the simulation that we only had one type of sediment which was similar to sediment 1 of case 1b. Yeah, so you can see that having these sediments and this mixture will affect on the behavior of each of these two sediments as well. Now, just for fun to finish this part, I'm going to also look at the instantaneous total transport. And I look for all fractions in red. So this is case 1b. And you can see this is case 1b for all fractions. And if I change to case 1a in black, we have only one type of sediment. And if I add that to plot, you can see that the sediment is about half the case 1b.